In this video, we'll be drawing and naming VSEPR structures for the VSEPR lab for Chem 111. Now, when we're drawing a VSEPR structure, it all depends on the number of electron units that are around your central atom. So we're only concerned with the central atom from our Lewis structure. Now, our electron units are going to be things like lone pairs on the central atom. So we're going to count the number of lone pairs, so not the total number of dots, but just the number of pairs of dots. Or our electron unit can be the atoms that are attached to that central atom. So again, we're not counting the number of bonds or the type of bonds, so we're just counting the number of atoms attached. So a single bond or a double bond or a triple bond, we're only going to be counting that number of atom attached and not the number of bonds that are there. For our electron geometry, this is going to be looking at all of the atoms attached and all of the lone pairs on our central atom when we are coming up with this name. For our molecular geometry, this is going to shift around based on the number of lone pairs, but it's coming up with its name based on only the atoms that are attached. So for our electron geometry, if our atom only has two things around the central atom, so two atoms attached, an atom and a lone pair, that will be 2 electron units. So it will have this sort of orientation where the atom is in the center and we've got one thing on either side. And this gets named linear. So if we have 0 lone pairs on our central atom, that means that both of these lines are going to connect to another atom. So we've got our atom in the center connected to 2 other atoms. And this shape is still, for the molecular geometry, there are no lone pairs on this central atom right here. So the name that it gets is described by the shape of the BAB structure, which will again be linear. If our central atom here has 1 atom attached and 1 lone pair, it'll look like this when we have our electron drawing. But when we're considering this molecular geometry, we don't draw the lone pair in. So we are going to have just A and B attached to one another, knowing that there is a lone pair over here on A. And again, this shape, if we look at that, that shape is still a linear shape. And we don't have any other lone pairs that we can put, because if we put another lone pair on this central atom, so both of these were lone pairs, we just have an atom by itself. Coming down now, looking at our 3 units around our central atom, so that could be 3 atoms attached, 2 atoms attached and 1 lone pair, or 1 atom attached and 2 lone pairs. We've got our central atom with 3 different things attached to it, and this shape here is called trigonoplanar. So if we go to draw this now with no lone pairs around our central atom, so all of these 3 lines here would have atoms attached with them, we still have the same shape that we started off with. And you'll notice as we continue to fill in this column, with the 0 lone pairs that our names are all going to be the same between. And you'll notice that the first column that we have here with the electron geometry is going to match this 0 lone pair column for our molecular geometry, so the names are also going to match here. We've got trigonal planar for our molecular geometry. Now if we've got one lone pair on here and then 2 atoms attached, we're going to end up with so this is what it would look like if we were drawing the electron geometry, where we'd have 1, 2, 3 things around our central atom. But when we're drawing our molecular geometry, we ignore the lone pair and just look at the picture that is made with the 1, 2, 3 atoms attached right here. And so this now gets a new name, and the name for this structure is going to be bent. Now, as we look at our 4 units attached, so we've got 4 units attached, we now see this new sort of way of drawing. So up here in our linear and our trigonal planar, we're just using lines. Now those lines represent atoms that are all in the same plane, so the plane of the paper as one another. When we've got wedges and then dashed wedges, this wedge is describing a shape that sticks out of the plane of the paper, and this dash is describing a shape that sticks back behind the plane of the paper. So as we fill in our central atom here, it could have 1, 2, 3, 4 things attached around it. These 3 would be in the same plane as one another. This one is sticking out, and this one is going back into behind the page. And this structure is called tetrahedral. So when we have 1 atom attached with no lone pairs around it, we'll have 4 things around. So again, we've got a wedge. So that B is coming out of the plane of the paper, and those dashes are describing this B going back into the plane of the paper. No lone pairs, so our names match between the electron geometry and the molecular geometry. Now, as we look at our next structure, or next with 1 lone pair, so we'll still have 3 atoms attached, and then we'll replace with 1 lone pair. So we've got our central atom, and it'll have 1 lone pair and the 3 atoms attached. And again, when we're looking at this kind of a structure here, we consider this in terms of the electron geometry, but when we are doing our molecular geometry, we erase the lone pairs before we assign the name. And the name for this one, because it has these 3 around the bottom, that gives it trigonal, and it sort of sticks up a little bit, so it's called trigonal pyramidal. Now that we have more possibilities going on with this structure here, we can actually end up in a situation where we would have 2 lone pairs on our central atom. So as we look at that kind of a structure, we've got our A in the center, and we could have a lone pair here, a lone pair here, and then our wedge sticking out, with an atom attached, and our dash sticking back with an atom attached. And then before we can come up with the name for this structure, for our molecular geometry, we're going to ignore our lone pairs and then just name what we have left. And the name for this one is going to be bent. And if we wanted to, we could redraw this where we just have everything in the same plane. So both of these two structures right here are equivalent to one another. This one right here is just making use of the wedges and dashes that we started off with in our original electron geometry. This one is also relevant though because all three of these atoms would be in the same plane as one another.